Yeah, I'm Carl Pearson. This work is in collaboration with some folks from the IBM T.J. Watson Research Center in New York, in the States, and also the University of Illinois, where I'm a PhD student. And so one of the things that we've noticed while working with various people doing HPC work is that they have some application, like Enrico did, and to understand and optimize their application, they kind of do some ad hoc performance measurements of some of the capabilities of the system. Enrico's talking about some data transfer measurements is what we were interested in too. And as nodes are getting more and more heterogeneous and complicated, doing these measurements is increasingly important and also kind of finicky and difficult to get right. And so we wanted to release basically a set of tools or a benchmark suite that would allow people like Enrico, who wanted to measure these interconnect performance, to just run this and have some pretty high confidence that they could get the measurement or the bandwidth measurement right on these different complicated system topologies. And so what I'm going to do is talk a little bit about the nodes, although Enrico talked about that a little bit, and then talk to you about the project. And the code is open and available, and you can download it yourself and run it. It's not quite ready probably for release, but we have people besides our group who are using it, so it's somewhat ready. There's some hope if you download it that you'll be able to build it and run it. And I wrote a 90-page master's thesis on all of the measurement results, so I'm not going to throw all that at you. I'm just going to show you some stuff. So, sort of in the past, back when, or near the time when I started my PhD, we sort of had GPU systems that look like this. So in blue, we have a CPU with some cores in it, and it's attached to a memory. And then there's some relatively slow interconnect that goes to a GPU. And the only reason this is relatively slow is because these days we can get ones that are much faster. And so, for example, we might have, on the Blue Water supercomputer in Illinois, we have a 16-core AMD CPU attached to a Kepler GPU with PCI, actually it's PCIe 2 on Blue Waters, but maybe a PCIe system these days would be PCIe 3. And in parentheses here we have the bidirectional bandwidth. So, but these days, you know, a node looks more like this, right? We might have two Power 9 CPUs, each with 20 cores, and 4-way multi-threading instead of 2-way multi-threading maybe. The GPUs are a lot bigger. The GPUs themselves have much higher memory bandwidth. Instead of DRAM, they use a different technology called high bandwidth memory. But importantly, also the interconnects between the GPUs have gotten a lot faster. And so understanding the performance of moving data, once we have workloads running on these different components of the system, the application is much more affected by relative communication performance between those different system components. There's a lot more system components to understand. And sort of alongside with that, the software is getting a little more complicated. So this is just a diagram trying to show different techniques of managing memory using CUDA's explicit memory management system. So this is not the unified memory management system. Basically, we have certain kinds of allocations shown in boxes here that can be on a CPU or a GPU. And so there's multiple different kinds of allocations that you can make on a CPU with different properties. There's different ways that you can transfer them to a GPU. Sometimes allocations, data that is physically on one place is implicitly or explicitly available on another place through different methods. And so each of these, in addition to the fact that the hardware topology affects the performance of the data transfer, the choice that you make at the system software level about how you're allocating and moving the data also affects the transfer bandwidth. So we'd like to understand this. And furthermore, you know, that's not even the only CUDA memory management system, say. So this is the unified memory management system where instead of explicitly creating allocations and moving them with APIs, we can create a kind of allocation that is implicitly available on both the CPU and all of the GPUs on the node. And it sort of moves data as you access it. It maintains coherence and page granularity. There's some nice features where we can say, if we know for sure, this comes with some performance penalty that I'll actually discuss, due to having to maintain some of the coherence properties of this data. But if we know some things about where we're going to be using data in the future, we can sort of hint to the runtime system, say, prefetch this data over to this GPU, and we can achieve some higher performance in that way. But basically, there's a lot of different ways to move data. The systems themselves have complicated topologies. We wanted to make the performance implications of this transparent to people who care about it. And so basically, what we've done is written a micro benchmark suite. Right now, it doesn't really have a name, so I'm just going to refer to it as like microbench or the micro benchmark suite. But essentially, it's NUMA-Aware CPU, GPU communication micro benchmarks. And right now, it can measure explicit memory management transfer techniques, unified memory management with coherence, which is where you sort of implicitly just access data and the CUDA system makes sure that you get what you asked for. And also with prefetch, where you give the driver some hints, particularly in very structured applications. This would be a good way to get some more performance. And the idea is that we wanted to kind of make it exhaustive. So with these different methods and with all the hardware that's on a particular node, we wanted to make sure that we could measure anything that people wanted to measure. And so basically what this looks like is pretty simple, but the idea is that we have sort of an outer loop over some number of benchmark repetitions to measure the variability. Sometimes we're on systems that are shared and we don't necessarily know if people in the middle of our run are coming in and doing some other work. This isn't such a problem if you're on a supercomputer or something, but when we just are getting access to a system, we say, hey, we're trying to test this software in your system. So we want to be able to make sure that we're getting some realistic numbers. But then the normal benchmark, there's like a setup and a teardown. And then in the setup, we're establishing allocations with particular properties and setting up the communication the way we want to measure it. We have a main loop where at first we ensure the data that we're trying to move is at the source. And the way you do that depends on the method, of course. And then we record the time that it takes to move the data to the destination. And we do this some number of times. I'll get to that in a second. And then, of course, we have the teardown. And what we're reporting is sort of the average performance that we observe over this loop. And then the ultimate metric is the average of the averages and the standard deviation of the averages, so you can get some sense of how variable this measurement is. And so so in addition to measuring the communication, we're also interested, this work is partially motivated by some neural network performance work that we're doing with IBM. So we're also interested in a variety of other CUDA primitive operations and neural network primitives that we've sort of extracted from the literature and networks that are out there. So this is kind of in progress too in the background. But in addition to measuring explicit memory management and unified memory management, we'd like to expand this to be able to measure in a controlled way some performance costs of if there's contention on some of these links, like Enrico mentioned. And there's various libraries out there to sort of handle multi-GPU communication collectives, so nickel. So for example, if I have a bunch of data on 4 different GPUs, and I want all of the GPUs to get the sum of all of the data. Instead of writing that yourself, which is tricky because of these performance characteristics, there's some libraries out there to do it for you, and since people actually use those, we'd like to measure those as well. We sort of kind of view it as an extension of the system software. And right now, this is all within a single node. We'd like to extend it to sort of network environments and also understand disk I/O. This is of particular interest in some neural network workloads where if we're doing an inference task, we might have a network stored on a disk and we have to get it into the GPU before we can do inference. That process actually takes most of the time. But for now, what I'm really talking about is none of this stuff, just the communication benchmarks. So one thing that we didn't want to do was write everything from scratch and then screw it up. So Google has a micro benchmark support library that they've open sourced that we take advantage of. And it provides some nice things. For example, it's easy from the command line to filter which benchmarks you want to run. That's important. In code, particularly in these cases where we're repeatedly doing the same task, the compiler can often tell that only the last iteration of that task is the one that actually does anything and will happily remove all the previous things that you're attempting to measure. So this provides some localized control of whether the compiler will do that or not, which is extremely important for this kind of work. It also has some nice utility functions where in this loop it can either automatically measure the time of that benchmark loop, but sometimes we don't want to measure the time because we don't want to measure the setup time in the loop. So you can do manual time. It also automatically determines the number of runs that loop should take so that it runs somewhere between 1 and I think 10 billion, and it makes it take a certain amount of wall time just so you don't make your benchmark go too long. But importantly, it makes it easy to do the runs in a repeated way and generate these simple statistics that we end up reporting. So we take advantage of this. This project is under active development still, which is nice. We also use CMake with something called CodeTire and Hunter. So basically, this is to automate part of the build. So CMake, if you're not familiar with it, it's sort of like a build configuration system. But basically, we use these tools to try to make sure that we can build it on Power 8 and Power 9 and x86 and ARM without too much trouble, because we're interested in being able to compare the performance of these systems. And another thing that we've done is we've created some Docker containers. So Docker, you can kind of think of it as a lightweight virtual machine almost, but basically it's a encapsulated environment where you can just run a particular configuration of our benchmark. So for example, if you're on Power 9 with CUDA 9.2 installed, then you can just run that one. You don't have to compile or build anything. It's just going to go ahead and work for you. Right now, we only have this for AMD64 because the one of the systems that we were testing on actually required that you run things through Docker. This is an NVIDIA DGX system, but there's no technical reason that we wouldn't be able to do this for ARM and Power. I just haven't done it yet. And one caveat is that Docker should probably have a network performance penalty because it does some virtualized network address translation, but it shouldn't have a performance penalty for any of the in-node measurements I'm talking about today. So we're not exactly sure how to manage this problem yet. Maybe it's just we'll have to measure it and report it or something.
Technically, you don't have to use virtual network, right? You can just go directly to the networking for the cross-node communication, so you basically end up with the same setup as an bare metal.
Okay, great, great.
Again, it may not fit your goals, but that's an option.
Yeah, I think that probably sounds okay. Okay, yeah. So we have So this is later in our roadmap. We're going to deal with this network stuff. So that's a good point. But yeah, so we just haven't quite gotten that far. Okay, great. And so we also have some associated code available to understand and plot the results, which is important. Right now they just get dumped as a bunch of JSON files with a lot of numbers in them, so they're kind of hard to read. But basically this is a Python package that knows how to interpret those files and can generate some plots, and it takes a custom plot specification format that we've developed and I'm in the process of documenting. It can generate dependencies, so it can be easy to integrate with a makefile. So for example, when I'm writing my paper, I include the data files in my paper, and whenever I build my paper with LaTeX, it generates these benchmarks on the fly, or the plots on the fly only if the data files are newer than the plots, that kind of thing. So that's kind of nice. But now we can get down to the results a little bit. So this is a so-called Minsky system. This is a Power 8 system with 4 GPUs. And it has NVLink 1.0. And it has these dual bonded NVLink lanes for this 80 gigabyte per second bidirectional bandwidth. And so this on your right is the sort of more modern version of that system. I think the code name is Newell, but it's 2 Power 9 CPUs and 4 Volta GPUs instead of Pascal. And another change is that they've upgraded to NVLink 2.0 with these sort of triply bonded lanes for 150 gigabytes per second bidirectional bandwidth. And Enrico mentioned this a bit, but we have the X bus here, which is 38.4 gigabytes per second on Power 8, and on the Power 9 it's 64. So the bandwidth between these GPUs has actually gone up by more than the bandwidth here has on the Power 9 systems. And we can definitely observe that in the results. One thing I want to talk about, and this is a PCIe system. This is actually NVIDIA's DGX system with Pascal GPUs. So it's sort of the same GPU as this, and on the left is the system, Power 9 system with Volta. We can see the y-axis goes up to 80 gigabytes per second here. And so these are the different data transfer methods that I was talking about. So this is sort of the traditional CUDA-malloc, CUDA-mem copy. This is if you do a different kind of allocation called a pinned allocation. I'll talk about the difference in just a second. But as we can see, this is this is unidirectional bandwidth now, so it's half of that bidirectional number. So as you can see here, the interconnects are getting faster, and at least we're actually getting some performance improvement from it. Though you can see that the sort of traditional CUDA-malloc, CUDA-mem copy, that's the yellow line, is actually not seeing nearly as much benefit as some of the other ones, though it is going up. And one of the interesting things that we observe is sometimes the performance is not so great. So this is just a CPU to a directly attached GPU on all of these systems. And so you can see that, say on this Power 8 system, the performance for these intermediate transfer sizes goes up pretty well, but then it drops down here for these large transfer sizes. We have a theory about why that is, but we're making this stuff available to IBM so they can figure it out. Although IBM's really more interested in the Power 9 systems now. But even there, they've got this weird little dip in their transfer system. And so one other thing we observe is that the affinity between the CPU and the GPU does affect the transfer bandwidth, and this is exactly what Enrico was talking about. So when I'm talking about local and remote, I'm saying whether the CPU and the GPU are directly attached or whether they're across the X bus. And so you can see that these two lines here, this gray and yellow, are CPU to GPU. This is remote and local. So actually, in this one, the remote is faster than the local. And on GPU to CPU, the local is faster than the, oh wait, no, sorry. Yeah, sorry, these are local transfers and these are remote transfers. So, yeah, the local transfers when the GPU is attached to the device, or directly to the CPU, is much faster than a transfer that has to go over the X bus. But depending on whether the transfer is local or remote, the direction CPU to GPU, the performance is actually which direction you're going is one of them is faster, one of them is slower. And the difference is not huge, but it's also not totally insubstantial. So these are kinds of things that we're exposing in these detailed measurements.
And this is the 4 GPU.
Yeah, this is the 4 GPU, this is the Power 9 system.
So it's 75 and 64 for the NVLink and the
Yes. Exactly, right. So yeah, the GPU to GPU should be 75, and the X bus CPU to CPU should be 64. And so this is coherence bandwidth between two GPUs now that are local and remote. And so for big transfers, the performance doesn't really seem to matter. For intermediate sizes, the local GPUs are faster. And if we use prefetch, so this is the unified memory system but with hints, then we can achieve sort of almost the same performance as if we use the old style explicit memory management. But where the affinity does have this huge effect on the achievable performance. And so part of the reason for this is that if we're doing a allocation from pageable memory, the way we would typically do this is we'd say, we're going to create some array on the host, and that's going to be in the application's address space, right in the CPU memory somewhere. And when we initiate a CUDA-mem copy to the GPU, what actually happens is that the driver takes this allocation here and copies it to a pinned internal buffer. And the difference between these two buffers is that this one, the application or the operating system is free to page out, so the pages may not physically be in memory at any given time, they might be on a disk. This one, that's not true. The operating system can't move it. And the reason that that's important is because the GPU is directly going to do a DMA, a direct memory access into this space, so these pages have to be there. When the GPU accesses them, they can't be on disk. But what you're going to notice is that there's this additional copy. When I try to do copy from the host to the device, actually I copy from the host to the host, and then the host to the device. So if I do a pinned allocation first on the host, I'm guaranteeing that this data will never be paged out. and I can just directly copy it to the device. And so what we see is that this actually has a pretty big performance impact. So this is the pageable one, again, and this is the pinned one. And so when we introduce that extra host-to-host copy, it really tanks the performance even on these new Power 9 systems. And conceptually, there's kind of, from a hardware perspective, not really a good justification for this much of performance degradation because the CPU DRAM bandwidth is around 100 gigabytes per second. So really, the performance shouldn't drop down quite this badly. And in particular, some of these copies from the GPU back to the CPU are just like really quite bad in the pageable one versus the
But
pinned
you
one.
have to, I mean, if you do the copy, then on the main memory, you probably read and written.
Yeah, that's true.
You know, so it's not like Power 8, right? Where there's the separate bus for read and write.
Okay.
It's the same bus.
Okay.
You know, for the 120 gig or so.
Okay.
So if you, for example, if you did 2 reads and 2 writes on that, you're at 30, right? 120 divided by
Sure.
4. No.
So this might actually explain something else that I observed then. So yeah, some of these results we are talking with IBM about because we don't really understand why they are. So I think maybe it's on the next slide actually even. But again, you know, it's not necessarily obvious from, you know, if I read the CUDA documentation, you know, it might tell me that the pinned copy is faster than the pageable one in some cases, but they don't really tell you, for example, that the GPU to CPU direction is going to be quite different from the CPU to GPU direction in some cases. So this is, you know, there's some reason to measure some of this stuff. Right, and so I showed this plot before, but depending on the kind of transfer you're doing, the CPU to GPU direction can be quite different performance from the GPU to CPU direction as well. And so this is actually another thing that I observed. This is if we invoke CUDA memcopy just from the CPU to the CPU. And we see on the Power 8 system that the performance in general is better than the Power 9 system, although for big transfers it's kind of small. But here in this intermediate size, where things might potentially be fitting in one of the large caches, there's a big performance difference. So we observe some of this stuff. So this might be getting at some of the things that you mentioned. But I think, and the other thing that was kind of cool that we're able to mention is we're able to measure the page fault latency on the GPU and between the GPU and the CPU. So this is when the GPU uses the unified memory system and accesses data that's resident on the CPU and a page has to be moved over. And so what we observed is that on the Power 9 system, again, the page fault latency was lower, or higher. And the way you can read these plots is that we essentially generate a linked list in memory, and there's a large stride between linked list elements. And so every time, and basically what we're doing is timing how long it takes to traverse the list. And so every time you add another stride to your traversal, you're sort of incurring one more page fault. And so you can see that the number, these things sort of linearly slope up pretty nicely as we increase the number of strides. And so the slope of this line is then the page fault latency, or the cost of serving that data in the unified memory system. And so one thing is that Power 9 has support for something called address translation services, which basically means that the Power 9 CPU should be, or the GPU on the Power 9 and the CPU can share page tables. And on our system, that's not enabled, and so it's possible that the sort of old style path is not as optimized on that system in anticipation of the fact that this new one will be much better when it's enabled. So I think this is a combination of it's not, in the CUDA driver we have, it's not enabled by default. I just got a word from NVIDIA about how to try enabling it, but I haven't managed to run those numbers yet. So some things that we learned, generally writing this with Google Benchmark was a pretty positive experience, but when you're doing multi-threaded benchmarks, there's no built-in way to synchronize different threads. So for example, if I want to do a memory copy using multiple threads, we have to manage the synchronization between the threads ourselves. And when I did that, I ended up using OpenMP, which incurs its own overhead costs that you end up measuring, so it's not quite ideal. But I also found that when the CPU time that your benchmark consumes takes up is much greater than the wall time. So if, for example, there's some driver process running behind the scene that also consumes CPU time, somehow Google benchmark gets confused about how much is a reasonable time for the benchmark to take, and so it needs some help deciding that. And another kind of inconvenient thing is that the benchmark functions don't take integer arguments. And so for example, if I wanted to create a benchmark to measure multi-GPU contention, and I wanted to pass in sort of an arbitrary set of GPU IDs, I can't just pass a set of integers into the benchmark directly. I mean, you could come up with some C way of doing it in a type unsafe way, but it's kind of an inconvenience. So right now you can download this and run it, and I'm working with some people at IBM to do that now, and they're having some success, so you're welcome to give it a shot. We should have the full release out sometime in the next few weeks, and I want to have some sort of example results from some systems as well. Then the next step will be to add collective communication and contention, and then we're working on some of this neural network stuff on the side, so we're going to add that in later at some undetermined time. And so one thing that we've heard some interest in here is about using this as a sanity check for system developers. So when I was working at IBM last summer, they were working on drivers for a system, and they introduced some bug where the GPU link got locked in the lowest clock state. So if you ran a test, the code would be correct, but it would just be slower than you were expecting. And if you had some kind of simple sanity check to test this stuff, sort of every iteration, then you can catch that kind of thing pretty early. Also, people who are interested in developing performance models for how their code is going to execute on particular machines, the actual performance that you get can be quite different than sort of what it says on the tin if you look at the specification of the machine. And so getting some empirical data to make those performance models more accurate, I think this could supply. So yeah, here's the micro benchmark suite and the plotting. Found some kind of interesting, surprising results that we're looking into more, and be happy to share or work with you if you're interested in trying to run this. If you have some benchmark that you're interested in, try to add it in, anything like that. Thank you for your time.